Good afternoon, dear participants. This is the last session of this FDP. So Dr. Sarfraz Hussain will be continuing with his demonstration of LT Spice. So over to Dr. Sarfraz Hussain. Thank you.
Yes, thank you, Apurva sir. So today we will be basically discussing about the designing of a two-stage op-amp. So yesterday we had seen how we can design a differential amplifier, and today I will also tell you how to find the values like mu and Cox values. So how we can calculate those values, and before going to this design of an op-amp, so we should know what are our specifications, because for a particular op-amp we should have a particular set of specifications. So here, what are the main specifications that we need is the load capacitance. Okay, so load capacitance value. So we should know this load capacitance value, and we should also know the slew rate. So what is our expected slew rate? And then gain, then unity gain bandwidth. So unity gain bandwidth basically gives us the bandwidth at which the gain is unity. Okay, or we say 0 dB. So these values we should know, and there are two more values, that is the ICMR positive and ICMR negative. So these are basically the common mode ranges, so positive and negative. So the positive common mode range actually give us the maximum input that we will apply as a common mode, and negative, that is the minimum voltage that we will apply. Now in this designing, there are two more specifications that we want, so VDD and VSS. So that we can actually choose like what do we want. So it can be based upon our model files or our requirements. So we can choose what will be our VDD and VSS, and based on that we should actually look into this. So ICMR positive and ICMR negative, so these will actually tell us that what should be our VDD. So if we are taking a ICMR of 1.6, so if this ICMR value, so if it is equal to 1.6, so that means we want a VDD which will be greater than this positive value. And if I take this ICMR negative, then a value that we will be giving here, okay, so the value that we will be giving here, so we should know that, okay, so here as you can see, so the VD saturation, it is near about 200 millivolts. So we will apply the saturation region like when the transistor is on. So we will apply that particular equation, that is the VGS is greater than VTH. So if I know the value of VTH, so let me just, okay, so there are some more values that we should know. So one is the VTH value and K value. So this can be Kn or Kp. Okay, and we should know the value of VTHN or VTH of P. So these values are to be known. So if we know these values, VTH of N, VTH of P, Kn, Kp, so these values if we know already, then we can actually put it into our equations. So either we can like we can use any mathematical tool such as Mathematica, or we can also use MATLAB. Okay, and we can just write down the equations, and we can do one thing, like we can just put the values of these into that equation, and we can just have a value of NMOS values and PMOS values. So we can find it out from that equation. So in order to design a particular op-amp, so these are the specifications that we want. So how do we know what is the value of Kn and Kp? So that I will tell you how we can find out the values of Kn and Kp. So let me open a new schematic. So suppose I want to find out the value of Kn. Okay, so that is the mu and Cox value of a N MOSFET. So what I will do, I will just put a NMOS over here. Okay, then I'll do the connections that is required. So suppose I want to connect the source and bulb to a ground node. Okay, so this should be actually like if you are connecting to minus of 1.8, then you should keep a minus 1.8 voltage over here, and if you are connecting to a ground, so you can make the necessary arrangement like that. So that will actually give the mu and Cox value of this one. So that will give you a rough estimate like what will be the value. So let's say that, okay, so this is just for an example that let me connect these two with the ground, and what I will do is that I will make this in a saturation region. So I will make this NMOS work in a saturation region. So I will connect the drain to the gate of this. So if the drain and gate are connected, so this will be in saturation region. Now we also have to check that this should not go into cutoff. So for cutoff, it should be like the VGS should be greater than the VTH value. So let me take a high value. So I will consider 1.8. So I am taking a high voltage at the input, okay, or we can say the maximum voltage at the input side. So I'm taking this as 1.8. So I now the VGS value, I am like I know already the VGS value. Then what do I need? So here, in order to find out the Kn value, so let me just write down the equation. What is the equation for the current in saturation region? So the ID formula is equal to, so this is equal to 0.5 multiplied by mu n Cox, or you can just write down K. Okay, so K dash, let me write down just K dash, and or let me, okay, so let me just write down as K mu. So 0.5 into mu n Cox value multiplied by W upon L, okay, multiplied by VGS minus of VTH whole square. So this is the formula. This is the formula for the ID current. Okay, so this is the formula for the current in the saturation region. Now I want to know the value of this Ku. So what I'll do, so Ku is equal to what? ID upon these values. So first of all, I'll put the value of W by L as 1 and 1. Okay, so let me put the value as 1, 1. So I put the value of this as 1, 1. Now I need to have the particular technology. So let me just copy the technology. Okay, so the location of the technology. So let me just copy it and let us place it somewhere above. So this is the technology, and the name of this particular transistor is NMOS1. So we'll just rename it as NMOS1. So we have this model from this particular library. Now we need to fix the W by L ratio. So let us fix it as 1U on 1U. Okay, so both are 1, 1. So length and width, so I have kept it 1, 1. So I have made this as 1, 1. This value is 1. And ID value, till now I don't know the ID value. Now VGS value and VTH value I already know. Okay, so VTH value I can just check into the model file, and I can just put the value of VT0. Okay, so in the VTH value, I can just put the VT0 value, and ID I can find out from the simulation, and in W by L I am already fixing this value. So this is equal to 1. So ID we will find out by the simulation. So how do we find out the ID? So we will click on this one. Okay, so simulate, we will run this one and find the DC operating points. Okay, so we'll click on this. So we'll basically find out the DC operating points. So we'll run this one. So let us just save this one as a test file. So I saved this one as a test file, and let me run the DC operating point. Now when I run this one, so I get a value of ID, right? ID value, I'm getting here some values of ID. So what I will do, I can also do one thing. I can just right click on this one, okay, and go to draft. Right click on this particular schematic window, then go to draft, and then go to this one, .op data label. Okay, so .op data label. So basically we will be labeling this one. So what I'll do, instead of just like searching for the current over and over again, so what I'll do, I'll just place it over here, then I'll right click on this one, and I will choose. Okay, so first you remove this $sign. Okay, and you can also put some expressions also as well here. Now I want the value of ID1 to be displayed. So I will click on this one. So ID of this transistor is displayed over here. Okay. So ID value is displayed over here. So we can just mark it separately. So we can just go to draw. You can draw a rectangle and just like we can just separate this one from the rest, and you can just select which line to choose. So ID value, so if you will change the value of W by L over and over again, so you can see there will be a change in the current. Now what you need to do is that here in this particular equation, we'll put the values of VTH, we'll put the values of W by L, and I will put the value of ID. Now when I put these values, I'll get a value of KU. Okay. So when I put this, when I do this one, so I'll get a value of KU. So which will be near about, I think, yeah, so we can just do that one, like we can just calculate that one by that, and it will be near about 100 to 200. So it will be near about 200 or something. Okay. So you can just do the calculation of this one, KU value. So once we calculate that one, so let us just quickly calculate that one. So if we calculate that, so 176.84 divided by 0.5, then this WL is 1, so we need not divide that one. Then divide the VGS value. So VGS here is 1.8. So 1.8 minus of this value. So this, let us consider that the value of the threshold is 0.4. So 1.8 minus of 0.4. So that is 1.4. So basically 1.4 square. Okay. So we'll divide this value. So it will come near about 180.44 microsieverts. So the value from this one, okay. So let me just, so the value of KU will be equal to 180.44 micro. So this is the value that we will get from this particular simulation. So we are getting the value of KU as this one. Now what we will do is that we will change the value of W by L in this particular transistor, and we'll put the value of KU as 180.44. Now if you do that, so if you put the value of KU as 180.44 over here, and suppose if you change the value of W by L, so since W by L was 1, so now if we change this one to 2, so we'll see what will be the difference in the current. So if I make this 2, so the current value should be doubled, right? So W by L was 1, so when I make this W by L as 2, so this current should get doubled. Okay, and this value only I'm putting over here. So with this particular equation, it should come like approximately, so this is 176, so it should come near about 350, something like that. So let me just change this one to 2. And you can just run this one. So as you can see, so here you can see that 347.48, right? So when we put the value of KU over here and we are changing this particular width, so we are getting a double value of that one. So that means for this one we are getting the particular result. Now what you can do is that you can change the value of VGS also and check what values you are getting. Okay, so if I change the value of VGS, let us say if I make it 1.4 and then I run it. Okay, so if I run it, so I'm getting this particular value. Now what you can do is that you can just quickly calculate using this particular value only. So 0.5 multiplied by 180.44 multiplied by W by L, we are keeping it 2, so we will multiply with 2, multiplied by this VGS is now 1.4 and minus of 0.4, so this becomes 1, right? So the square of 1 is 1 only, so we need not multiply that one, so it comes near about 180.44. okay, so it is coming near about 180.44. So that means we are getting the value. Okay, so if I run it, So the simulation is giving us 197.61, and when we calculate it manually, it gives around near about 180 point something. Okay, so we can just choose this value accordingly. So now, since we know that the value is important, right? If I put this one, so instead of this like 181, if I make this 181, so it will increase, right? So 0.5 multiplied by 181 multiplied by 2. So this will give us 181. Okay, because multiplied by 2 means what? So if I make this near about 9, right? So if I want to 2 multiplied by 0.5 is nothing but 1 itself. So that means this ID, okay, so whatever current we are getting, so it is mainly because of this only, that is the K value. Okay, so we'll not make it too large because there are some other parameters that are also affecting it. So we can just make it up to 90. So Ku value we can put as 190. Okay, and then we can know that okay, K equal to 190, and we are getting the ID current this one. So by putting this K value as 190, we can check if we change this one. Okay, so if we change this one to 1, so what is the value that we are getting? So we are getting near about 100. Okay, so 190 divided by 2 will give us what? So 190 divided by 2 will give us near about 80, right? So 190 divided by 2, so this is actually equal to 95, and here the approximate current that we are getting from the simulation is 100. So that means if we choose K value equal to 190, so that will give us a closer value. Okay, so this is how we can just try to figure out like what will be the mobility value. Okay, or we can say that this will give us the K value. Okay, so this Kn and Kp and Vth and Vtp, so this we can find out from the Vt0. So from that Vt0 we can take, and if we are considering the Vthn max, then we'll add 10% into that. So, and if we are considering the minimum value, then we will subtract 10% from the Vt0 value. So this is how we can find out the K and Kp value. Now, how to start with the design of an op-amp? So there are different people actually have different approaches for the designing. Okay, and you can actually design this one. So what you need to do, you have to first decide what or how you will start, whether you will start with the first stage or whether you will start with the second stage. Okay, first you have to decide from where you need to start the designing. Okay, so there are two ways, like you can either start with this one, then you can come back to this one also. Now for this one, what I did is that I have chosen 100 microampere current which is flowing through this particular differential amplifier, and 100 microampere current which is flowing through this particular common source amplifier. Okay, so I'm considering 100 microampere for this one and 100 for this one. So where did I get this current value? So this I can calculate it using the slew rate also. So if I choose a particular slew rate, okay, so slew rate is equal to I into the capacitance value. Okay, so I here is 100 micro. So 100 micro multiplied by the capacitance value, so 1 pico. So like that you can calculate it, and you'll get the current value. So from slew rate, we'll get the current value. So what current value we want, or what biasing current do we want here. So once we get the current value, okay, so this we can get it like we will get the slew rate values. So this will also give us a slew, and this will also give us a slew, because here also we have a capacitor, here also we have a capacitor, and this is actually dependent upon this. So we'll consider this particular capacitance, that is the feedback capacitor over here. Okay, and this capacitor we will use it to find the slew rate. So we'll use this particular capacitor value, and this current will be multiplied with the capacitor. So this will be actually equal to, so slew rate will be equal to I5 multiplied by Cc. Okay, So I5 multiplied by Cc. So from here we will get the value of I5. Now when we get the value of I5, okay, we have got the value of the current that we want, that is supposed to be used as a biasing current. Now what will the currents through these branches? So it will be halved. Okay, so it will be parted into two parts. So 50 microampere will flow from this particular branch and 50 microamperes will flow from this particular branch. Okay, so now we have fixed up to this one. Now the next thing that we need to fix is the VD sat value. Okay, the saturation point. So this saturation point will actually decide the lowest output swing. Okay, so this saturation point will be our lowest output swing. So we will fix this one to a certain value. So for this case, I have fixed it to 200 millivolts. Okay, so this value you can also like choose according to your needs. So here how we can choose that? So what you can do is that you can first use this property. Okay, so V bias and VSS. So you can give a biasing voltage over here. Okay, you can give a biasing voltage over here, or you can just calculate it using the VGS. So here what happens is that for VD sat value, so let me just write it. So at VD sat or VD is equal to VG minus of VTH. So VD sat, so this is equal to VG minus of VTH. So let me just zoom into that particular area. Now VD sat is equal to VG minus of VTH. So this will be our bias voltage. Okay, so this will be our bias voltage, and VG value should be greater than VTH. So that also we know. Okay, now what value will decide the current? So here in this case, you can just so the current in the I5, or we can say the bias current. Okay, I bias will be equal to 0.5 multiplied by the Kn value that we can find out. Okay, like I said, multiplied by the W by L ratio. Okay, so W upon L multiplied by VD sat value. The power. So I bias will be equal to this. Okay, I bias is equal to this. So we know the value of Kn, we know the value of I bias. Now there are two unknowns. So either we can choose a particular W by L, or we can choose a particular VD sat. Okay, so VD sat we can also choose, okay, from the input common mode range. Okay, so input common mode range, from there also we can find out. So one condition for the VD sat is this, that VD sat should be greater than this VG of 5 minus of VTH. Okay, so this is one of the conditions, and another condition is this. So how we can find out that one? So the VG of 1 should be greater than VTH, right? So this is the minimum condition for the transistor to be turned on. So VG1 should be greater than VTHN, or sorry, VGS of 1 should be greater than VTH of n. Now the VG is what? VG is the minimum voltage, right? So minimum, so we can write down V minimum minus the S. So Vs is nothing but VD sat. So this value, VD sat value, this value should be greater than VTH of n. Okay, so now this minimum, so whatever input voltage, okay, so the minimum input voltage that we know, so we will have to put that particular value over here. So in our case, so let us say the minimum input voltage that we are considering over here. Okay, so the minimum input voltage, it can be like it will be more than that one. So we can either fix, so if it is 200 millivolts, so this plus of 0.5, so it is near about 0.6. So let us consider that the minimum input voltage is 0.8. Okay, so if I consider that V minimum is 0.8, so VD sat should be lesser than 0.8 minus of this value. So 0.8 minus of 0.4. Okay, this is the VD sat value. So VD sat, so 0.8 minus of 0.4. So basically VD sat value should be lesser than 0.4. So we can choose any value which is lesser than 0.4. So if I have that choice, so now I have fixed the VD sat value as 200 millivolts. So once I choose the VD sat value as 200 millivolts, so I can use the particular equation. Okay. So in this case, so VD sat value I am getting 0.4. So this is, so VD sat should be lesser than 0.4. Now I will choose the VD sat value as 200 millivolts. So if I choose VD sat value 200 millivolts, so now here VD sat value I already know, Kn value I have already calculated, I bias we already know what will be the bias current. So we can easily calculate the W by L ratio for that particular transistor. So now we have got the transistor specifications for this particular transistor, that is the M5. So we have got this particular value for this one. And we also have a bias voltage, so we can just apply that particular bias voltage depending upon the VD sat value. So what will be the bias voltage if we set this one? So V bias should be, so it should be like VD sat is equal to VGS minus of VTH. So it should satisfy this particular result. So VTH value is 0.4, and so this minus of 0.4, so that should be lesser than this value. Okay, less than or equal to this particular value, that is 200. So 200 value greater than this one. So the VTH value is 0.4. So the minimum value of V bias that we can put is 0.6. So we can put 0.6 over here. Okay, this is the minimum bias value that we can put over here. So these are the things in this one. So or you can also calculate it like this, like you can put some lower value, but the VD sat value will be always constant because of this bias current. Okay, so now once you have fixed this particular portion of the design, now we can go for the designing of M1 and M2 transistor. For designing the M1 and M2 transistor, what do we require? So for designing this particular transistor, here we what are known to us, so the current is known to us. Now the amplification, or we say the gain of this particular amplifier, it is actually dependent upon the transconductance or the GM of this NMOS transistors. Okay, so what value should be put for the transconductance of this one? So we can use this formula, that GM square is equal to, like we can put that particular formula, or what we can do is that we can calculate the GM value from this formula. Okay, gain bandwidth product. If the gain is given to us, suppose if the gain is given to us, say the gain of the particular differential amplifier. Okay, this is for the differential amplifier multiplied by the CS amplifier. And suppose say unity gain bandwidth is 10 megahertz. Okay, so suppose we have the gain and we have the unity gain bandwidth. Now we will multiply the gain of this one. So 100. Okay, so this is the gain of this particular differential amplifier, and the other 100 or the other half is for the particular second stage. Now we will multiply these two, 100 multiplied by 10 megahertz. So we will multiply the gain and the bandwidth, and this is equal to what? Gain bandwidth product is equal to GM upon twice pi CC. Okay, so let me just write down over here. Okay, and here we should remember that it should be twice pi, like we need to add the twice pi also. Okay, so we will write down, because here we are calculating the frequency, so that is why twice pi value will also come over here. So let me just write down. So Gm is equal to GBW multiplied by Cc, and here it will be twice pi multiplied by this value. Now we have got this particular value. So Gm is equal to twice pi GBW multiplied by Cc. So gain bandwidth product, so we already have from this particular equation. We already know the value of Cc. So Cc, how we can calculate? So we can calculate from the slew rate equation. Okay. Or we can also calculate like Cc is equal to 0.22 times the load capacitance. So from there also we can calculate the value of Cc. So once we know the value of Cc, so we can put in this particular equation and we can find out the value of Gm. So once we get the value of Gm, we can find out the value of the transistor size. So how can we calculate the transistor size? So we can use this equation. So like actually different people use different type of equation, and I use this particular equation. So W by L of 1 will be equal to Gm square, okay, Gm square divided by our current, okay, so 2 multiplied by I1 multiplied by Kn. So this actually gives me the value of the W by L of 1. So I1 value, it is nothing but half of I5 value. Okay, so this is equal to 50 microamperes, as we have seen what will be the current in the branches. Kn value we have already calculated, so we'll put the value of Kn, we'll put the value of I over here, and we'll put the value of transconductor, that is the Gm, from this particular equation. Now once we have put these equations in line, so we get the value of W by L. So once we get the value of W by L, so here we are getting the value of W by L for these two, that is the M1 transistor as well as the M2 transistor. Okay, so we have got these values. Now once we have got these values, then next is what? Next we'll design this one, M3 and M4. Okay, so for M3 and M4, how we can do that? So here, like we can either do in two ways. Okay, so here are like two options that we can choose. Either we can use this one, like the minimum criteria for this PMOS to be on. Okay, we can use that particular criteria, that is the VDS should be greater than VTH. We can apply that one and we can find out the values. Okay, and what we can do is that here the current value, we already know the current value, right? So this current value we already know, so we'll use this current equation for this particular transistor, that is the PMOS one. So for this M3 transistor, let us put the current equation. So current equation, if you put, so here what will happen? So VSG, okay, so VSG should be greater than VTHP. So this is one of the conditions. So let me first write down the current equation for this one. IST for the M3 transistor. So this is equal to same 0.5 multiplied by Kp. Okay, so in the same manner, we can also calculate the value of Kp. So once we have calculated, we can put in this value, and W upon L multiplied by. So here we'll put Vd, so VSD. Okay, so VSD square. Now here VSD, so VS is what? So here it is 1.8. So VSD means VDD. So VDD minus of VD. Okay. So this gives us the value of VSD. So VSD is basically equal to VDD minus of VD. So we have got this particular value. Now D. So VD value will be what? So how can we calculate the value of VD? So here, as you can see, the VD of this particular M3 transistor is also the drain of this particular transistor, that is the M1 transistor. Now here, how we will find out? So VD is equal to VGS minus of VTH for this one. Okay. So what is the VGS value? So here we will find out the VGS value and VTH value, and this will give us the VD value. So let me write down. So VD is equal to V input max. Okay, V input max. So the maximum ICMR value, so that will consider as the V in max value, and this V in max value we will subtract this one. So this minus of the VTH value of the M1 transistor. So this will give me the value of VD. So this V in max value, so this we will get from this particular like design, and we can just put it there, and we can subtract the value of the threshold. Now when we do that, we'll get the value of VD, and we'll put in this equation. So here VDD value we already know. VD value we can calculate from this equation. KP value we can calculate like we have calculated for the KN value. And ISD value, so this is already, we know that this is 50 microamperes. So we'll put this value over here. So easily we can calculate the value of W upon L. So now we can calculate the value of W upon L for these two. So we got the value of W upon L for these. And what I did is that I have made these as variables over here. So for capacitor, as you can see, these capacitors, I have put the CC inside a third bracket, and I have saved it as a variable. And for the different transistors, I have made it as W3 for both M3 and M4. I have kept the width as W3. I have kept the length as 1 micro. And in NMOS, I have made these. Okay, so the length I have kept it 1 micro, and the width I have kept it W1 for both of these. And here I have kept it as the length is 1 micro and the width is W6. For this one, it is W7, and lengths I have kept it 1 micro. You can also choose a lower value of the length as well. So it actually depends upon the like how you want to calculate, because W by L ratio, you already know the W by L ratio, so you can make the necessary changes accordingly. So if like whatever values I'm getting, so if I want lower values of width, so I can reduce the size of the length. So if I reduce the size of the length, so or I can like make some changes. So based on the W by L ratio, we can do the necessary changes in the width and length. So now we have got the values for this differential amplifier. So once we have got the values of this differential amplifier, now we will try to find out the values for this M6 and M7 transistor. Okay. So here the current that we are expecting over here is 100 microamperes. Okay, so let me just write down here. Okay, so here I'm biasing and I'm keeping the transistor size. Okay, so I'm just changing it a little bit. Okay, so when I'm like, if I bias this with the same bias voltage and I'm keeping the transistor size same as this, okay, so the current that it will draw is 100 microampere. So 100 microampere current will be drawn from this particular transistor. Now, what are the values that we already know of in this particular transistor? So, or we can do a matching also. Okay, so matching, how we can do? So this current and this current, this width and this width. So we can just do this kind of matching. Okay, so the current flowing through this divided by the current flowing through this. So it will basically be twice of that, right? Because this particular current is twice of this current flowing through this one. So we can use that particular property. Okay, we can use this matching property, that whatever current is flowing through this one, so it is okay. So this current is half of the current that is flowing through this one, and we'll try to match these two. So this PMOS and this PMOS, so we'll try to match these. What is the length of this one and what is the length of this one? So we'll just try to divide those things. Okay, so basically what we'll get, so basically I6 upon I4 will give us S6 upon S4. Okay, I6 upon I4 will give us the value of this. Okay, the transistor size or the dimension or the size. Okay, so we can say S6 or we can use the word D for dimension. So the dimension of M6 upon M4. So we already know the value of M4. Okay, we know the value of I6, we know the value of I4. Okay, so these two current values we already know. What will the current through this one, what will the current through this one. We know the transistor size of M4, so we can easily calculate the value of M6 over here. So now we have got the values of M6, M7. Okay, M7 is just like the transistor that we have used in this one. So M7 and M5 we are keeping it same biasing current. Okay, see here we are giving it 100 microamperes, so that's why I'm also like, since I am considering that 100 microamperes is flowing through this one, so that is why I'm keeping this same. But this value can differ. Okay, so when we'll choose a different gain, so here if I'm choosing 100 gain for this particular stage and 100 for this particular stage, so that is why I'm keeping the same bias current over here. But you can also change this one based on the gain value, so the current value will also change. So if there is a different current value over here, so since the bias point is same, and this V out swing, okay, so the output swing, if it is, let us say if I am keeping it to 170 or 200, so this VD sat value, I already know what will be the VD sat value. So from that VD sat value and our current specification, I can find out the value of the transistor, this M7. And M6 value we can just find out through the matching property, that the current in this one and the current in this one. So I6 upon I4 is equal to the dimension of M6 upon M4. So this will give us the value of this transistor. Now once we get all the values of these transistors, then we will do the setup. So in this setup, we will put the VDD value, we will put the VSS value, we put the bias value, and inputs we will change according to our requirement. Now in this case, I am keeping the common mode voltage as 1.2. Okay, so why I am keeping it 1.2? Because the upper limit to this one I am taking as 1.6. Okay, so let me just okay, so the maximum value I'm keeping it 1.6 and the minimum value I'm keeping it 0.8. So the point in between these two is 1.2. Okay, so 1.6 minus of 0.8 is 0.8. So basically we add 4 to 0.8 or we subtract 4 from 1.6. So basically the middle point between these two input ranges, okay, the middle point between these two common mode range is 1.2. So that is why I'm keeping this common mode voltage as 1.2 over here, so that I will get a good output. So now I have kept the common mode voltage as 1.2, and now I will check for different types of simulations. So what are the simulations that we will do for the op-amp circuit? So the simulations can be a transient analysis, AC analysis, DC analysis, noise analysis, transfer function, or just the operating points. So let us first start with this one. So transfer function, so what do we get from the transfer function? So transfer function, we will get the values of the impedances. So basically the input impedance or the output impedance. So if you want to know the input impedance or the output impedance, so you can directly do the transfer function analysis. So TF you can do and you can get the impedances, that what will be the input impedance, what is the output impedance. So you can directly calculate from that one. Now let us start with the first analysis. So let us do the transient analysis first. So in the transient analysis, we'll choose input. Okay, so we'll choose both the inputs. Okay, okay, first let us just try to have a pulse. Okay, so since this common mode input is 1.2, so we'll vary this one. So let us say it is from minus of 0.4 to plus of 0.4. Okay, so I'm just taking a small, so just 100 pico, 100 pico, 100 pico, and 100 and 220 n, and let us say 4 cycles. And I'm running this transient analysis for 400 nanometers. So okay, so this is my input and output. So the VIN, okay, so this I'm keeping it constant. So this is equal to the common mode range. Okay, so this VIN is the common mode range, and this is the V input. So whenever this V input is high, okay, so when it is greater than this VIN, so I should get a high output, and when this is lower than this, so I should get a low output. So let us add another plot plane, and we can add traces. So in the traces we can use this, so V out. So you can see V out value. So here for this one, okay, so when the VNP is greater than the V input value, so V out is 1, and when it is lesser than, so this V out value, so it goes down. Okay, so it is having a lowest value. So the lowest value here we are getting it minus 1.7999. Okay, so minus 1.79, so it is near about 1.8. And here you can see the highest value as well. So what will be the highest value? So this will be equal to 1.8. Okay, so 1.78 it is showing. So 1.78. So this is the highest value that we are getting for the V output. Okay, so the V output is swinging from minus 1.8 to plus 1.8. Okay, so this value it is swinging from here to here. Okay, so just 1 minute. Okay, so we have done the transient analysis. So why we do the transient analysis? So we do the transient analysis to find out the slew rate. So let me rerun it again. So as you can see, the output is slewing down, right? So it is slewing from this point to this point. So if you want to find out the slew rate for this one, so what we'll do, you find out the points. Okay, so the highest point that we have, so from 1.8, okay, or what you can do, the next thing that we can do is that we can choose a 0.9 value of this one. So let us say we choose 1.6. Okay, so let us just have this one as 1.6. So from 1.6, so now I will click on this one to have a second cursor, and from 1.6 to, let us say, 1.4. Okay, so let me choose a value that is equal to 1.4. Okay, so somewhere near about this one, so I have 1.4. So what I'll do is that I'll see how much time it is taking and what is the difference in the voltage. Okay, so the difference in the voltage and the difference in the time will give me the slew rate. Okay, so let me just write it down over here. So slew rate is equal to BO1 minus of VO2, okay, the output difference divided by the time difference. So basically T1 minus of T2. Okay, so slew rate is equal to this. So V, okay, so V01, V out 1 minus of V out 2 divided by T1 minus T2. So the output voltage. So here I am considering this as 1.6. So I will write down here 1.6. Okay, so this. So this will be what 1.6 minus of the lowest one I am taking 1 point minus of 1.4. So minus of minus means this will become plus. So this is plus of 1.4. Okay. Now this value will be divided by T1 minus of T2. So or we can sorry T2 minus of T1. Okay, so T2 minus of T1 because the time of this is greater than this. So let me say that it is 160 minus of 120. Okay, so I am just writing it roughly 160 minus of 120. Okay, so I'm getting this value. So 1.6 plus of 1.4 divided by 160 minus of 120. Okay, so this comes near about 2, 3. Okay, so 3 divided by this is 40. So 3 divided by 40. So you can calculate it. So 3, 7. So it is near about 7 something. Okay, so near about 7 point something you will get. And since it is nano, so in nano, so you have to multiply it by this. So you will get this multiplied with 10 to the power 9. Okay, so when you will multiply that one, so let me quickly do that one. So 1.6 plus of 1.4, so this is equal to 3 divided by 4, this is equal to 0.75. So 0.75 multiplied by this value. So this will give me near about value. So 750, we can say 750 mega. Okay, so 750 mega volts per nano, or we can say that yeah, so per nanosecond. So what is the value in per nanosecond? So 0.75 or 750 millivolts. So here I can write down 750 millivolts per nano. Okay, so 750 millivolts per nanosecond. So this is the value that we'll get. Okay, so based on our design, so it varies based on our design. So I have not actually designed according to our 20 megavolt. Okay, so that is why it is differing. So you can just calculate like this. So 750 millivolt per nanosecond. So you can have your own slew rate, and based on that one, you can define. So this is how we calculate actually the slew rate. Okay, so the maximum point of this one and the minimum point of this one, and we just subtract this one and find out the dV upon dt value. So dV upon dt value will give us the slew rate for this one. So this is how we get the slew rate. Okay, and this is how we do the you can say the transient analysis. This is why we do the transient analysis for the op-amp. So the main reason for doing the transient analysis is to find the slew rate for this particular case. Then we can also do a DC analysis. Okay, so let me show you a DC analysis of this one. Okay, so if we do the DC analysis, so you can see a output in this form. Okay, and we can also put the input and output. So here you can see, so when we do the DC analysis for this one, okay, so I'm getting a output in this form, and input and output are crossing at this particular point. So since I have set it to 1.2, okay, so I have taken the common mode range as 1.2. Okay, so this will be the midpoint for the common mode. Okay, so for my input maximum and input minimum, the midpoint is 1.2. So that is why, according to my design, it is setting up at 1.2. So here you can see the V in negative. Okay, so it is at 1.2. So whenever my input, okay, so VIP is crossing this particular point, so I am getting a high output. Okay, so the V out will become high if it crosses this particular point. So if I zoom it, you can see that it is crossing. Okay, so the value, okay, so the value that we are getting, so this V out is deviating from this 0 point. So this value, the deviation, okay, the deviation of the output from the exact point, that is 0. Okay, so the deviation from here to here is the offset value of this particular op amp. So this is how we calculate the offset. So we do the DC analysis to find out, or we can say to calculate the offset of this particular op amp. So this is how we can calculate the offset of this op amp. So we need to know the cross section point. So once we are done with the DC analysis, then we can go for the AC analysis and noise analysis. So noise analysis also we can do, and I will also show you some more values to it. Now let us do the AC analysis first. So let me just run the AC analysis for this one. So when I do the AC analysis, so I will click on the output voltage. Okay, so here you can see, okay, so first of all I need to change my inputs also. So here let me change it to a sinusoidal signal. So in this one, let us just rearrange this. So DC offset value, so let us put it 0, and this one, let us say it is 5 milli, and let us take the frequency as 100. Okay, so I'm considering the frequency as 100 kilohertz. Okay, and amplitude I am taking 5 milli. Okay, and I can also put like the same voltage over here, and I can do this. So let me just this one and copy paste this one, and I can have a negative input at this particular point. And okay, so when I put a sinusoidal signal, okay, so here I get a curve like this. Okay, so here I'm getting a curve like this. Now I can run my measurement tool. So I can just go to this one, and I can just use the dot measure file. And if I use the dot measure file, I can easily calculate what will be the gain. Okay, so I can see what is the gain, what is the 3 dB gain, what is the unity gain. Okay, so UGB, we can get it. Okay, so unity gain bandwidth, so it is near about 9.68. okay, so 9.68, so this is e to the power 7, so this is in mega, so that is 96.8 megahertz. So at 96.8 megahertz, the gain is 0 dB. So here also, like manually also we can check. So 0 dB, you can check 0 dB, so it is near about this point, and it is equal to 9.6. okay, so this is the unity gain bandwidth. And if you want to find out the bandwidth for this one, then you have to find out the 3 dB point. Okay, so from, suppose this is V out is this one, so the gain of this one is 75.44. so now the gain, we know that it is 75.44 dB. So we have to reduce it by 3 dBs. So 75 minus 3 is 72. So we'll go to this one and we'll find out that 72. Now at 72, we'll check what is the frequency that we are getting. So 40 kilohertz, that is the frequency we are getting, and the cutoff frequency we can say it is equal to 40.5 kilohertz. Okay, so that will be our cutoff frequency. So at 3 dB minus 3 dB frequency, we can say the minus 3 dB frequency is 40.5 kilohertz. Okay, so this is the minus 3 dB frequency over here, and the gain, or we can say the 3 dB gain is this one. 72 dB is the 3 dB gain. Now if we want to find out the unity gain, so what we'll do, we'll go to the point where our gain is becoming 0 dB. So let us go to the point where it is 0 dB. So if we go here, so near around this one, okay. So when we are near about this one, so you can see over here, so 96.8. So we can use the dot measure file also. We can create a dot measure file. We can use the particular script dot measure and we can evaluate that one. So when we evaluate that, so we can directly know the value, or else we can just directly know from this. Okay, so manually if you want to calculate, then you can just move this particular cursor and you can see that what is the frequency at this particular point, that is the unity gain bandwidth. Okay, so this will be the unity gain bandwidth. So this is the UGB at this point. Now if you want to find out the phase margin and gain margin, that also you can find it out. Okay, and like what you can do is that, so you need to keep a marker at 180. Okay, so where the phase is 180. Okay, so the phase is 180 at this point, so you need to calculate the gain at this point. And the at 0 dB you can have, so what is the phase at 0 dB? So you can see here the phase is 210. So thereby if you subtract these two, so there is 30 degrees. So that is why, since the phase margin is 30 degree, okay, so that is why this system is unstable. So we need to have, okay, so we need to have a phase margin that is greater than 60 degrees. Okay, so we need to have a phase margin that should be greater than 60 degrees, then only our system will be stable. Now this system is not stable because the phase margin is lesser than 30 degrees. Okay, and if you want to see the pole of this system, then what we can do, we can just disconnect this capacitor, so we can see the second pole also. So we can see the second pole clearly. Okay, so here the drop from here will give us the first pole, and then there is a minus 20 dB per decade slope. Okay, so 20 dB minus 20 dB you can move from here, and then you can see there is again a drop in this one. Okay, so the gain, you can see the gain curve. So this is moving from here, and this is the next point, and then it is again moving to this one. So when there is a drop, okay, or when we say that there is a pole, so you can see there is a phase shift of 90 degrees. So there will be a phase shift of 90 degrees. Then again you encountered a pole, so then there will again be a shift of 90 degrees. So total there is a phase shift of 180 degrees. So here you will again get a phase shift of 90 degrees. Now you are getting this particular value. So we need to have this phase margin. Okay, this should be, the phase margin should be like 60 degree or greater than 60 degree, then only your system will be stable. So for that, like, you have to make some more adjustments to this one. So what adjustments can we do? So let us put back the capacitor again. So let me put back the capacitor again. So let me rename this one again as CC. Now our system is still not stable. So what we can do is that we can actually put a resistor. Okay, so we can put a resistor over here. So the first, this differential amplifier is having one pole, okay, and the second CS amplifier is having another pole. So that is why we are having a two-pole system over here. And since it is like I am having a pole that is crossing the like that is in the imaginary axis, so that is why it is becoming unstable. So in order to move that particular pole towards the left hand side, I need to add a resistor over here. Okay, so by adding a resistor, I'm adding you can say a 0 to it. So now if I add a resistor, okay, and let me change this value. So let me put it first 1K, and you can observe the difference. Okay, so when I put it like this, so when I keep the resistance as 1K, so you can see this phase is changing, right? This particular phase is changing. So now you can see what is the difference in this one. So 180, and you can also draw from here that at 0 dB, what is the phase, and at 180-degree phase, what is the gain. Okay, so like that you can calculate. So at this 0 dB, so what is the phase? So it is near about this point, and this is, so 180 minus of this, you can calculate it. Now as you increase this particular resistance value, so what will happen? Okay, so as you keep on increasing this value, you can see that the system that you're getting somewhat like this. Okay, so there is a pole that you're getting somewhere here. Now this pole, I don't want it to be here. I want this pole to be below this 0 dB point. Okay, I don't want this pole to be above this 0 dB. I want this pole to be below this 0 dB, so that my system becomes stable again. So what I'll do, I'll change my resistance value. Okay, since 100K is too much, so I will reduce this one. I'll make it 1K. Okay, since it is moving, so if I keep it 1K, so then also I'm getting this one. So like this also you can do. You can just keep on changing these values and see which will give you the stable value, or you can just directly calculate from the formula and you can find. So let me put this as 1K, and let me change the value of the coupling capacitor. Okay, so this one, so coupling capacitor, so I can change this one. So if I reduce this value, so if I reduce this value, so this pole is decreasing, right? So or let's just keep it in this. Okay, so you can see this pole, it is going down. So as I am increasing this one, so it is going down. So like that you can do this one. So if you need to adjust, you can do the adjustment accordingly. Okay, so according to the requirements, you can just adjust this one. So there are a lot of things to do in LT Spice actually. So these are some of the design examples, like how we can simulate a two-stage op-amp using a LT Spice, how we can actually use this to perform, okay, for the designing of all these parameters, how we can do the exact designing of this particular op-amp circuit, and how we can find out the values. And these parameters actually I have kept it. So these are actually the data points that I have selected, and these data points, so you can also do like this, like right click on the schematic, go to draft and click on .op data label. So when you click on this one, so it will basically label those particular data. So whatever data you want to display over here for your own analysis, so you can just put it over here. So I hope like it is clear up to this one. So we can move on to the next part. Okay, so we have seen how we can do the transient analysis for this one. We have seen how we can do the AC analysis for this one, how we can do the DC analysis. So AC analysis, basically what we do, so in AC analysis, we are doing for finding out the phase margin, for finding out the gain margin, to find out the gain. Okay, so these are the things that we want by using the AC analysis. Now there is there is another kind of analysis that is called as the noise analysis. So how can we do the noise analysis? So for doing the noise analysis, we can just go to the simulator window and we can look for the function. Okay, so let me just show you. So go to the edit simulation command. Here you'll find out this noise. Okay, so here in the output part, you have to put the value of this output. Okay, so you have to just write down V of V out, then input. So that will be your input voltage. So here I have considered this one V1 as the input voltage, and you can choose the switch. So you can choose octave, decade. So depending upon your requirement, you can choose that one, and the frequency. So now let us do noise analysis. Okay, so once I click on this one, so you can see the noise over here. So at lower frequencies, you can see the flicker noise. Okay, so at lower frequencies, you can see this noise, and it is decaying, right? So as we are moving this particular, like we are going towards a higher frequency, so this is decreasing. So you can get a graph. Okay, so you can get this noise values from this one. Okay. Now, if you want to check the noise for a particular resistor, okay, so if you want to know the noise of a resistor, you can just click on this one. So when you probe on this one, so you'll get a noise of this particular resistor R1. Okay, so let me just remove this first. Okay, so this will actually show you the contribution of this noise. And if you want to find out the noise of this capacitor, so you can click on this one. So let me just rerun this again. Okay, so this value R1 value, so you can see over here. Okay, the R1 value you can see at lower frequency, so it is 1.95, so this much nanovolts. Okay, so this much nanovolts. So we can. So here you can draw the gain and frequency, and where is the resistor? Okay, yeah, here also you can see there is a V input noise also is there. So you can also plot the input noise also. Okay, so you can also see what is the input noise, and you can keep on like plotting in different plots also. So if I want to, so here as you can see, this is the noise of the resistor. Okay, so this is the noise of the resistor. So how much noise resistor is contributing, so that you can see that this much amount of noise is being contributed from the resistor. Now what we can do is that we can also make this noiseless. Okay, so we can make this resistor noiseless by clicking on this one and writing noiseless over here. Okay, so once we write noiseless over here, and if you run it, then you can see there is no noise by the resistor. Okay, so this is gone. Okay, so this is gone because there is no, so if you don't want any noise contribution from the resistor, okay, so if you don't want any contribution of the noise from the resistor, then you can make it noiseless. Okay, so you can just write down this noiseless. Okay, so you can just write down the transistor value and space, give a space, and then write down noiseless. So that will make that particular resistor noiseless. Okay, and this is the resistor which is having a noise. So this is how we can actually check for the resistor. So whatever resistors you are using, you can check the noise contribution by the resistor. You can also check the noise contribution of the transistors as well. So if you want to check for the transistors, so you can also check. Okay, so here you can see this V of M2. Okay, this is the noise contribution of the transistor. So for each of the transistors also you can see what is the noise contribution from that particular transistor. So these are the things in this one. So this is how we can find out the noise contribution from this. And then we can also do this one, like we can do the transfer function. Okay, so DC transfer function. So in the DC transfer function, what we can do is that we will have the output and the input. Okay, so only these two inputs are required. So we'll put the output and source. So when we do that, okay, so let me just run, and it will give you the values. Okay, so basically it will give you the input impedance and output impedance. So let me just show you. So once I run this one, so you get a transfer function value, okay, this impedance value, and you get input impedance and output impedance. So the input impedance for this op amp is this, okay, and the output impedance you can see is this one. So this is near about 80 kilohertz, and the input impedance is you can see it is very large. Okay, the input impedance for this particular op amp is very large. So these are the simulations that we can do for the design of a two-stage amplifier. Okay, so for a two-stage amplifier, so all these simulations we can do using the LT-SPICE command, and these actually show us a lot more ways how we can analyze a particular amplifier. So if you want, so whatever gain we are getting over here, these are basically the open loop gain. And if you want to find out the closed loop gain, or if you want to calculate the common mode rejection ratio, and if you want to check the power supply rejection ratio, so for these things, what we can do is that we can make a symbol for that one. So we can make a symbol for this two-stage op amp, and using that particular symbol we can analyze it. Okay, so we can just give a feedback. So we can give a feedback to the op amp, so to the positive, and so there are a positive and a negative end. So we'll give the, if it is a inverting, so if you consider this op amp as inverting amplifier, so you'll connect that to V in, and you will give a feedback resistor to it, then you check. Okay, so these things we can do, like how to check, and if there is an offset. So for like for removing the particular offset, what you need to do, you just need to add a particular voltage equivalent to that offset. So if you add a particular voltage equivalent to the offset, then in the particular circuit you will be removing that particular offset value. Okay, so these are the things in this one, and I hope it is clear up to this, like how we can design and how we can analyze all these values. And for the differential amplifier also we had seen. So, and for this design also we know that how we can do this. So if there are any queries from the participants, please let me know that what else you want to simulate, or if you have any queries regarding the design of an op amp, so you can ask me. So you can ask me, and like you can also type in the message box. So like, is it clear like how we can design it? See, there are different ways actually, because like some people, how they design is that they will start with this one, okay, the first stage. So I already shown you how we can start with the first stage and go to the second stage, and then we can do the designing. Now if we want to design from the second stage, okay, suppose I want to design it from the second stage, then how we can do it? So for that one, the slew rate that we are getting, so instead of this I5, I'll use this I7, okay, and I will see what is the load capacity over here, and I will apply that particular current, that what is the current that is required through these transistors. Now when I get to know about these transistors, I will design this transistor first, okay, I'll get this particular value, then I will design this particular transistor, that is the PMOS circuit. So in this one, so what will be the input? Okay, so that we actually need to decide. So for designing the second stage of the amplifier, we actually need to know what is the middle, or we can say the common output swing of this particular differential amplifier. So if we already know the output swing of the differential amplifier, then what we can do, so we can design the PMOS accordingly. So suppose the output swing of the like differential amplifier, so it swings between 0.2 to 1.6. Okay, so the differential amplifier output, it is swinging from 0.2 to 1.6. So the midpoint between these two will be used as a voltage, or we can say the gate voltage for the PMOS, that is the M6 transistor, and we will use that one, and current value we already know, so then we can easily design the PMOS circuit. And once we are done with that one, then we can go back to the first differential amplifier circuit. And so the main important thing is to find out the currents. Okay, and we can also measure the power distribution also. So here the power distribution, if you are, suppose I run this one, let me run the transient. Okay, so let me just change the values of transient analysis. So let me So as you can see, so here, so let me draw these in different plots. Okay, so we can draw this into two different plots like this. Okay, so now I want to calculate the power distribution. Okay, so I can just add a new plane, and I want to know the power distribution. So for power distribution, what I need to do, so I will click on Alt, and I will bring this thermometer symbol near to this VDD, and I click on this one. So when I click on this one, so I will get the VDD into IDD curve. Okay, so now I need to find out the average power. So I will press on Control and I will click on this one. So this will give me the average power distribution. Okay, so this is equal to 362.59. Okay, so here the current, so here it is showing minus 362 because I'm taking the opposite one. So I'll just make this one as minus of this, and then let me take the average of this one. So here you can see it is 362.59 microwatts. Okay. So this is how we calculate the power distribution from this one. So you can directly calculate, like even you can do the DC analysis, and then also you can calculate this part. Okay, so if we do the DC analysis for this one, then so you can calculate the power, DC power. Okay, so let me just do it like this. So this value of power, it is the transient power. Now if I want to calculate the DC power, so we can have the DC power. Okay, so here if I calculate it, so here you can see it is 278 microwatts. Okay, so these are the things in this one. So basically whatever we want to do, like whatever values we want to calculate, so we can calculate like this. And if you want to draw the symbol, then we need to just copy this one. Okay, so suppose I want to make a symbol from this one, and then I want to use this particular test bench. So what I will do, I will just create a new schematic. Okay, then just copy this one. So why I'm doing this, because if I want to do the common mode rejection ratio, suppose I want to do the CMR, or I want to find out the common mode rejection ratio and some other parameters. Okay, or we can say the feedback. Okay, so I want a feedback of this one. So like that, if you want to use, so then we can do this one. So let me just remove this load capacitor from here. Okay, and let me put this coupling capacitor as, or let me just remove this coupling capacitor and resistor. Okay, so let me just remove this. So this is a simple op-amp circuit. Okay? So I'm considering only the simple op-amp circuit, and here I will have this input-output ports. Okay, so VIN, VNP, V bias, V out. So these are the ports I am considering. So now what I will do, I will create a symbol for this one. So for creating symbol, first save this particular file. So let us save this as op-amp SC. Okay, so let me just save it in the name of op-amp SC. So I have saved this file as op-amp SC. Now I want to create a symbol for this one. So what I will do, I will again go to file. Okay, so first I need to give the this particular circuit the pin port name. Okay, so here the port name are also already set. Okay, so these are the levels already given to this. So VDD, VNP, V bias, V out. So already we have given the name to these particular ports. Now I want to make one symbol. So I'll go to new symbol, and here I'll put the name of the port. So what are the ports? So VIN, VNP. So let me just place it VIN, VNP, and V bias. So I will click on. So if I press P, so this window will pop up. So once this window pops up, so you just write down. So VIN P. Okay, the positive node. So this will be on to the left. Okay, I am keeping an offset of 10, and I am writing it this. Okay, now I want to have another pins also, so I will click on this one. Okay, so I will press P, and I will write down the pin port name. So VIN, I'll keep the offset as 10. Now similarly I can add, okay, other ports as well. So here, before drawing this one also, like we can also do one thing. We can just minimize, and we can have a particular symbol for this one. Okay, so if you want to draw a particular symbol for this one, so you can use a line, and we can just like this. Okay, so here if we can draw, so 1, 2, 3, 4, 5, 1, 2, 5. So this will be 1, 2, 3, 4, 5. So here. Okay, so we can draw like this, and we can bring these inputs here inside this one. And we can also write the input pin VSS. Here we can have VSS. Let me move this VDD pin somewhere near to this. Okay, so we have VDD, VSS, we have VNP, VNN, VIS, and we can put an output pin. So output pin, the name of the pin was V out, so we'll write down V. Okay, so this is the V out. So we can just change the offset. Okay, so as you can see, since we are like giving some offset to it, okay, so we are increasing the offset, so we are making a distance from this point. Okay, so like that also you can do. So you can just increase the offset in order to move this one further here. So now once we have created this one, then we can save it. So let us save in the same name as this one. Let us write down. Okay, so yeah, so I've written this one. So opam underscore sc. Okay, so I've created a symbol for this one. So this is same as this. Now what I'll do, let me just close it. So now what I'll do, I will replace this particular circuit with my symbol, and let me see if I'm getting the desired results or not. So let me just let me just copy this one and paste it here. So let us just close this one. So in this one, so we'll replace this with the symbol. Okay, so we'll replace this one with the symbol. So let us just remove this one. So we have removed this part, and let us replace it with the symbol. So how we can go to the symbol? So just click on the component, then browse towards the folder that, or you can say to your workspace, click on this one. Now in my workspace, I have this one open. Okay, so here you can see the symbol that we have created. So you click on this one. So now we have this particular symbol. Let us just click it over here. Okay, so similarly, we can like make different op-amps, different components of op-amps, and we can just keep on pasting those, and we can evaluate different things. You can also design a comparator. Okay, so you can also design a comparator. You can design a non-inverting amplifier, or you can also design some other kind of an amplifier, some differentiator. So these things you can make out of an op-amp. So once your design is complete, okay, so if your op-amp design is complete, then you can go for designing. So this particular circuit, so you can just put a feedback resistor over here. Okay, and you can analyze the outputs. So let me just first name these outputs. So VIN. So this one is PNP. This one is V bias. Okay, so and these two VDD and VSS, we need to write down these as well. So VDD. And this one, we can just right click on this one, change the name. So this is VSS. Okay, so VDD, VSS, VN, this one. So now let us run this particular simulation for this one. We can just click on this output and you can see that we are getting the same results. Okay, so we have basically created a symbol for this op amp. And if you want to do different simulations, so suppose I am doing a let us say I'm doing a transient simulation. Okay, so let me do a transient analysis and let me connect a feedback resistor to this one. So let me just extend this one and connect the positive node to the ground. So okay, so let us save this one as another file. So opamp underscore sc underscore test. So now if I want to connect this one, so I want to make it non-inverting feedback circuit. So I will connect this one. Okay, I will connect a feedback resistor over here. So let me have a feedback resistor. I'm connecting a feedback resistor, and here if I want to connect a load resistor, so that also I can do. So let me put a load resistor over here, and at this particular point also, like if I want another resistor, so I can do that as well. So the input side I want another resistor, so let me do that better. I'll just drag these ports. Okay, so for the timing, let me just remove this load. Okay, and here also, let me not put so many things. So here I need a bias voltage, so let me just keep it like that. VDD, VSS I want, VIN and VNP. So here in this one, so let me make this VNP ground. So let me just use a DC 0, and I will connect this one to ground. Okay, so I've connected this one to ground, and this is the sinusoidal signal that I'm giving. So input I'm giving to this. So let me just change this one to 5, and this is the common mode voltage. Okay, and so input is going through this and that, and so these values we can put it. Okay, so we can keep any values for this one. So for the timing, I'm just writing it like this. Okay, so I'm just taking an arbitrary value for this one, and I just want to run a simulation on this. So okay, so here I have this, so I can just check the input. Okay, so you can see there is some lag in the input. Okay, so we'll just change this one. Okay, so let us have a good input this type. Okay, and let us click on the output. Okay, so you can just separate these two, that will be much better. So the output will plot it into the other plane. Okay, so here you can calculate, okay, or you can do the calculations like what will be the gain and all those things. So you can calculate that. And here you can see these graphs. Okay, so basically the main reason of this is that, like, you can simulate and run and you can find out the common mode rejection ratio. Okay, for finding out the common mode rejection ratio, what you need to do, you need to like connect these two, that is the VINP and VINN. So you have to connect all these two to a single point. So if you connect all these two to a single point, then you'll see the difference. Okay, so then like the output should be zero. So if we are giving the same voltage, okay, so suppose if I am not giving any voltage to this one, okay, so suppose say VNP and VN both are same, so that means we are giving a common voltage to both of these. So let us see what happens then. Suppose I connected like this. So the voltage, okay, so if we are giving a 0 volt, so that means it is short circuited. So always remember that. So wherever you want to do, so you can try out this one and you can see that if V in and V out are equal, so you won't get any output. So there will be only a common mode point at the V output stage. So this point, so 1.12, okay, so here you can see both VIN and VNP. So here VIN voltage is 1.2 and V out voltage, so it is also near about 1.2. So it is 1.17. Okay, so this shows that like the common mode, okay, so both of these are same, and this difference in the voltage, okay, the difference in the input and the output voltage, so this difference is actually the offset voltage. So this offset voltage you can add it. Okay, so if we add this particular offset voltage, then we can say that okay, now you can apply some other inputs to it and it will show you the correct results. And yeah, and one more thing that we can do is that suppose if we have any variable in a particular design, we have a variable, and if you want to display that particular variable in form of a graph, okay, so that also we can do it. Okay, like we can change the width of a particular transistor and then we can check it in the form of a graph as well. So suppose say like if we have a particular equation, so that also we can do it. Suppose say I have a equation, okay, and let us say this particular equation, so SR is equal to I5 into CC. Okay, so I have this particular equation. So what I will do is that I will just copy this particular voltage. Okay, so I'll take a voltage. Okay, I'll take a voltage and I will rename it. Okay, so in place of this DC value, okay, so let's just close this one. So instead this DC value, so I will write down SR. Okay, so this SR value, so here we can write down, so SR is equal to what? So I5 multiplied by CC. So I5 also, for displaying I5 we can use a particular value. So this ID of M5. Okay, so we can write down this ID of M5. So let me write down here ID of M5. Now what I can do is that, so I can use the dot. Okay. Okay. So in this dot parameter, so what is the equation that we are looking for? So here, let us say id of or I5. Let us just write down I5. So I5 is equal to id of M5. Let us see if it is recollecting this value or not. Okay, so it is actually not recollecting this value. So what we can do is that, like, we can select a particular parameter value. Okay, so this value actually id value, I5 value, so this needs to be referred to first. Okay, so these values, suppose say I5 is equal to slew rate divided by this one. So slew rate is how much? So slew rate, let us say the value of slew rate is 20. Okay, and the value of CC is, okay, so we can just write down as this. Now if I run this one, okay, and I click on this, then it should show the voltage. Okay, so let me check. So this will be I5. Okay, so suppose, like, the main reason is that, like, if you want to plot this one, okay, so see here you are getting this value, so V is equal to 40. So if you want to plot any equation, so the main reason is that why I'm showing you this is because if you want to plot any equation, so suppose you want to plot any equation, suppose here it is I5 equal to this or any other equation. So what you need to do is that you have to state one parameter. Okay, so state any of the parameters over here. You can give a name to this particular parameter. You can write up that particular equation, and after writing that equation, so these values, okay, so whatever values that we are calculating in this particular circuit or anywhere else, so that we can put in this one. So suppose I want to plot the power, so what I can write, so power is equal to B of VDD, okay, multiplied by this I of V out. Okay, and here let me just write down this one as power. Okay, so can resolve this one because it is not taking the values. Okay, so it is actually not taking the value, so that is why it is not showing it actually. And but we can actually do that one. So we can just put any parameter like this. So here, if I am choosing any parameter like this, so once it calculates these particular values, so it will connect to this one. So this variable that we are choosing over here, so it will actually calculate from this one. Okay, so here VDD value is this. So let me just first let me just write down only this part. Okay, so it is not taking this particular value. Okay, so V of, so that means, okay, so for this one actually I need to use, I think, that measure file. Okay, so for this one, because parameter will only execute a particular equation having a particular value, because parameter, whenever we using, so we need to add a particular value to it. So that is why it is not doing that one. So in place of that one, we can use the part that is dot MEAS. Okay. So we can use dot MEAS, and from here we can measure the power. So for power, we can just do like this. Okay, so real name. So here we can write down power, and in the energy text we can write down the parameter. So in this parameter, so we can write down B of VDD. Okay, so if I write it like this, then let me run this one. So now I should get yes. So unknown parameter power will come. Okay, so in place of this one, let me just write down only power. Let me just take this one as this. So measuring power, so we can do this one. So dot measure power, so parameter VDD. So actually there are things like this, like we can use this measure. So measure will actually measure the power of this one. Okay. So here actually it is failing, so that is why it is not showing maybe. Okay, yes, so that is actually the problem over here. So let me take it. So parameter V of VDD of 1. No form data available. Okay. So let me just run this one again. And let me check the error log list. Yes, so it is showing me the power VDD of 1. So it is not showing me the correct value of this one. So I think there is something wrong with this equation. So power is equal to VDD1. So this actually should show me the voltage VDD of 1, but it is not showing me the value of VDD1. Okay, so let me do this in another way. Okay, so let me choose this as a transient analysis. And from this analysis, it will calculate the V of V out. Okay, so it is calculating the V of V out. So let me just run this one. So still it is not showing. So basically, like we have to give, I think, from the parametric analysis. Okay, so we have to use that dot param. So if we use that dot para and then we include the values, or if we put in any separate equations, then we can do that. And if we want to run that one, so then also we can use this kind of a source, and we can just place any values. Okay, so suppose if you want to calculate power, so if you want to plot, so whenever you want to plot any variable, so what we do is that we use this kind of a voltage source and we place the equation in here. When you place the equation in here, so it will show us the values, and we can plot that particular value. So these are the things that we can actually do using this one. So I think like that will actually help you when designing and when you need to verify these files. So that will be great. And if you have any queries regarding this one, please let me know about these. So if okay, so let me just look into the message box, and if you have any queries regarding this session, So it will be like good to share. So okay, Manjula, okay. Thank you, Manjula, and you covered a lot. If you have any manuals, kindly share. Okay, yeah, I do have some manuals regarding the LT Spice. Okay, so that I can actually share with the organizers. So I do have some like LT Spice tutorials on this one. But the thing is that like whatever I have covered in this particular sessions, like in these 4 sessions, so a lot of the things are all distributed form. Like you will find few things in some different books, or you will find something in some different ones. But I will share that. Okay, so Arup Shankar Bhaumik, share over the classroom Google. Okay, 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 okay. Yes, that also I can do. So in the classroom Google also I can do. But I guess it will be better. Like I will, because I have those files in a PDF format. Okay, so basically those tutorial files I have in a PDF format actually. And if you want these files, then also I can share it. And like basic LT Spice programs are there actually. I have with me with the basic LT Spice programs, and like you can go through the quick start, and there is a flyer for the shortcuts also. Like you can look for the shortcuts. What are the shortcuts? And most of the things that I have covered actually, like there is not a single PDF where you will get all those things. And if you want to know about the commands of this LT Spice, then you can like use that one. Like if you want to know about LT Spice, then you can go and check for the help which is provided here. So you can just click on this help and you can view the help topics. So here you can get a lot of details about the LT Spice actually. So here, like whatever functions you want to use, or these dot measure commands and all those things, so these all you will get it here in the help task. So there are a lot of things to cover in that one. Okay, thanks. Can we have your email ID for any query? Yes, sure. For any query, you can just let me know. Okay, I'll share my email ID as well. So you guys can let me know. So if you get stuck in any part, like if you want to do a particular simulation, so then you can let me know. And like for Monte Carlo and all, I don't have any PDF and all those things. Like that actually I searched in the internet, and somehow I came across that particular files. Okay, so I just came across those files, and then I saw that yes, there are 2 options to those Monte Carlo analysis. So in Monte Carlo analysis, there is an inbuilt function, and you can use that inbuilt function with that tolerance value. Okay, so in the Monte Carlo inbuilt function, just you have to put the nominal value and you have to put the tolerance, and it will calculate the it will do the Monte Carlo analysis. And if you want to check for the worst case analysis, so you can use the dot function variable. So by using that dot function spice directive, so using that one, you can actually build up some more powerful functions. Even if you can try, you can make for PVT analysis, and even the, like if you want to vary temperature. Okay, so suppose you want to vary a temperature, or if you want to vary any other parameter, so temperature also you can vary in this particular, like here. So like you can vary temperature, so just you need to call the dot. Okay, so in that step param, so you have to like suppose this is there. So when we do the step parameter analysis, so dot step param, then you have to write down this temp. So what this will do is this will actually vary the temperature. So the parameter that you want to sweep is the temperature. So here you can give some values to this temperature. So suppose one is 50 degrees, another is 100 degrees. So like that also you can do. So you can actually vary the temperature like this. Okay, you can check the output, you can vary the temperature, and you can check here also. Okay, so for the particular step, you can check the outputs. So step 1, step 2. So you can actually view the spice netlist also. Okay, so error log, you can use that error log to view the particular step. Like if we change the temperature, so what will be the value? So there are actually a lot of functions in LT Spice, and many are using this. Like LT Spice, you can say it is used vastly nowadays, and it has many applications. And since it is monitored by analog devices, like it has been implemented by analog devices, so you can find a lot of model files also. Suppose you want to, like you are looking for an op-amp circuit or ADC or any other circuit, if you are looking for, you can go through the analog devices website and you can get those particular like model files from their website, and you can run those model files, you can go through their data sheets, and you can make your own circuit design actually. And there are some more things, like suppose op amp also, like there are, if you go to this particular component part. Okay, so I'll show you this one. So here, if you go to this op-amp part, so here there are some op-amps which are universal op-amps. Okay, so you can also choose these universal op-amps, and let me just show you one just once. So in this universal op-amp, as you open this one, you'll see these values are already given. Okay, so the gain value, then this phase margin, and all those things are already given. That what is the slew rate, what is the gain bandwidth. So you, if you want to use this particular op-amp for a particular gain or anything, so you can just use this particular ideal op-amp circuit in your like if you want to use some op-amps. So for that one, you can utilize these particular circuits. You can put some gain variables in this one, and you can actually do that. And there are some more parameters in this one, so you just need to look into these components. And in this particular technology, that is in this particular software actually, LT Spice, you have multiple number of, you can see just for the op-amps only, you can see so many number of model files are there. There are lots of model files present here. So like you can just go through. So here you can see rail to rail FET input amplifiers is there. So a lot of like design circuits are there. So ADCs also, like there are a lot of ADCs. Okay, so these all ADCs are all analog devices, ADCs, and you can just make use of that one. You can even like try and find out those parameters of an ADC also. Like if you want to calculate the effective number of bits, if you want to find out the errors, okay, and like bit error rate, if you want to calculate a bit error rate, if you want to calculate the signal to noise ratio. So these all things you can calculate. So there is an option. So there also you can calculate. And here some NISC are also there. So you can, if you want to use a battery or cell, so that is also there. So that means that like there are lots and lots of options present in LT Spice. So you can make use of this one if you are using any like open source software. Okay, so if you are using any open source simulation software, so I would say that if you use LT Spice, then you can explore a lot in this one. So thank you so much for listening, and I hope you have gained a lot in this particular sessions. You have learned the tool, how to use that, and you can start designing by yourself. You can design your particular circuit, and you can do those simulations. So there are a lot of options. So basically AC, DC, transient. So these are some of the common analysis that we do, and you can also look for those poles and zeros. Okay, so these are the things in this one. Okay, thank you so much for listening.
Thank you, Dr. Sarfraz Hussain, sir.
Okay, thank you, sir. Thank you, sir.
My sincere gratitude to you.
Okay, thank you, sir. Thank you so much for
You have
this
conducted
opportunity.
4 sessions.
Yes, yeah, it has been really lovely sessions actually. Like I really enjoyed that. So
Yes.
these were 4 sessions, so it really took a lot of time. But there are a lot of things to explore in this one actually, LT Spice. And like there are, like I tried to cover as much as I can in these sessions actually, like whatever, like about the tool actually, not particularly about the designing part, but I think most of the things I have already covered in this LT Spice tutorial. So all those things, like whatever simulations that we can do and what are the things that we can do, so all those things are covered in these